Hey everybody, welcome to Mammoth Interactive's YouTube channel. First of all, I want to thank you for watching this video. And remember that this channel doesn't do Patreon. Instead, we sell our digital courses down below. And every single dollar that we get from the products you buy below goes into making more content. The best way to help out this channel and Mammoth Interactive is to subscribe to Mammoth Interactive's huge library of content. Get thousands of hours and hundreds of courses for a low price down below. We have a monthly option and a yearly option. Thanks for listening, and I'll see you in the video.
Hello everyone, and welcome to our Python interview questions course. In this lecture, we're going to be introducing all of the topics covered in this course, as well as previewing the different interview questions we're going to be covering. Not only will you learn how to solve interview questions, you'll also learn the thought pattern, you'll learn how to recognize thought patterns, you'll learn the best way to answer each question and how to approach topics in various types of questions, and you'll also learn about time complexity and space complexity. Let's go ahead and introduce the different topics. So we have 10 different sections here, beginning with section 0. We have fizz, buzz, and time complexity. We're going to be answering one of the most common interview questions that is very well known, fizz, buzz, and we'll also be discovering time complexity in depth. So we're going to look at the types of time complexity and algorithm examples of each. The time complexity you need to know, as well as big O notation. Then in section 1, we're going to look at our first set of interview questions in the string and array category. This is arguably one of the largest categories asked about, so strings and arrays are number 1. We're going to cover topics like reversing words, rotating arrays, looking at isomorphic strings, and finding the kth largest element in an array. All of those questions, we're going to define all of the terms you need to know, as well as how to approach the solution and build out a running solution. And of course, we will have all source code for you at the end of each section. Then in section 2, we are going to look at matrix interview questions. This includes questions like setting matrix zeros, finding the spiral matrix, and finding the number of islands. Another commonly asked, extremely popular question is the number of islands. So we'll be getting to all of those, and we will have questions of different difficulty levels. That way you can see exactly where you are at in terms of being able to pass the test. In section 3, we are going to answer linked list interview questions. We will solve questions like implementing a stack, adding numbers, and reversing linked lists. Then in section 4, we're going to look at the binary tree data structure. This course is going to be covering data structures and algorithms, the most common ones you need to know for the test. So with binary trees, we're going to learn how to traverse trees in order, pre-order, and post-order traversal, the most common traversal ways you need to know, as well as solving the maximum path sum interview question. Then moving on to section 5, we will be solving graph interview questions. We're going to learn how to build a graph as well as find the largest component in a grid. In section 6, we will be looking at sorting. We are going to cover the most popular sorting algorithms you need to know, as well as the time complexities of each of them. We're going to look at these sorting algorithms from worst to best. So this includes bubble sorting, selection sorting, insertion sort, quicksort, merge sort, all of those. In section 7, we're going to look at dynamic programming. This is a wide topic because there are many different types of questions you can get implementing dynamic programming. So we're going to look at dynamic programming as a whole, and then look at some of the most common questions you will be asked with dynamic programming. In section 8, we're going to look at bit manipulation. Bit manipulation will allow you to build extremely efficient and clean solutions. So if you can master bit manipulation, that will definitely show your skill at the test. We're going to cover questions like first introducing all of the bitwise and shift operators you need to know, as well as solving questions like the single number, finding the single number in an array, finding the number of 1 bits, otherwise known as the Hamming weight, in a question, and more. Now, we will be covering all of the terms you need to know, so not to worry about that. Depending on your difficulty level, you will either need to learn all the terms with us, or you can go ahead and go through all of the questions with us. In section 9, we're going to look at combinations and permutations, interview questions concerning those. These two terms come from math and they are extremely important to know because the two are easily confused, but you should not confuse them. So in section 9, we're going to solve questions like finding permutations, finding distinct permutations, as well as the common question finding the letter combinations of a phone number. And then finally in section 10, we'll be looking at math interview questions. If you can understand math and how you can apply math to solve these interview questions, you'll be able to create extremely clean and efficient solutions that will be very impressive. So of course math is a huge topic. There is a lot you could potentially cover. We're going to be introducing the concept of math, the patterns you should recognize, and why math is so valuable, and where you can recognize the ability to use math instead of something slower like iteration or recursion or even sorting. So math is extremely efficient. We're going to answer questions like reversing integers, finding palindrome numbers, and the popular Excel sheet questions. Alright, so let's go ahead and introduce the browser IDE we're going to be using, the Integrated Development Environment. That is known as REPL.IT. This here is REPL.IT. It is a completely free website and you don't even need an account. You can just click on Start Coding and you can immediately begin coding. That is all you need to know to get started in this course. So let's go ahead and move into the next lecture where we're going to be solving our first interview question, the most common one, fizz buzz. See you there. Hello everyone and welcome back to our Python interview questions course. In this lecture, we're going to solve a question that is almost synonymous with coding interview. That is the fizz buzz interview question. The question goes, print the numbers from 1 to 100, and for multiples of 3, print fizz instead of the number, and for multiples of 5, print buzz. As you can see, we have an output of 1 to fizz because 3 is a multiple of 3. Then we have 4 buzz instead of 5 because 5 is a multiple of 5. And you'll notice that at 15 we have printed fizz buzz instead of fizz or buzz. Why? Well, because this is an edge case. 15 is a multiple of 3 and 5. So we must print both fizz and buzz. With every question that we solve together, you'll notice that checking for the edge cases is extremely important. You always want to account for any weird cases, undefined cases, or disallowed values. And we'll be doing that throughout the course. So let's go ahead and solve this problem together. We're going to need to use a loop that will begin at 1 and end at 100 inclusive. So we'll say for number in the range of 100 to 101, because if we only did up to 100, then the 100 would be exclusive, so we would have forgotten about the final buzz at the end. So now that we have the header for the for loop set up, what we're going to do is check if a number is divisible by 3, 5, or both. And of course there's many ways to solve each problem, some more efficient than others. So we're going to do the check for if the number is divisible by both first. We're going to check if the number mod 15 is equal to 0. This means that the number is divisible by 15. The modulo operator will divide a number by a value and return the remainder. If the remainder is 0, that means that the number is a multiple of 15. And any number that is a multiple of 15, it automatically is also a multiple of 3 and 5. So what we're going to do in this case is print fizz buzz. And we can also add a character break in between each of the values. And then we're going to continue. Next, we'll check if the number is divisible by 3. So if the number mod 3 is equal to 0, then we're going to print fizz as well as a break. And after that, we can check the next case. If the number mod 5 is equal to 0, that means the number is divisible by 5. And in this case, we have to print buzz, just as the question asked. And we'll continue. And it's easy to forget the last step, which is to print the number itself if it is not divisible by 3 or 5. In that case, we must print the number instead of anything else. So we'll print the number and we'll add a character break. And just like that, we have solved our first interview question, the fizz buzz question. Let's go ahead and test this out. We will pull up the console here and we will hit run. As you can see, we have being printed 1, 2 fizz, 4 buzz fizz, 3 is a multiple of 3, so we have fizz, buzz is a multiple of 5 because it represents the number of 5. All the way up to buzz, which represents 100, which is divisible by 5. And you'll also find that for values like 15, we have fizz buzz being printed. That is exactly what we expected, which means that we successfully solved this interview question. And of course, with every question, you can test with more cases. Typically, this would be if you had an input. You could check with many different inputs to validate your result and to make sure that the input worked with various inputs, that your solution worked regardless of the input. In this case, we were not given an input, we were only told to output. Alright, the time complexity for this question is going to be linear. Now, if you don't know what that means, we'll be discussing time complexity in the next lecture, so not to worry. But the time complexity is linear because it is directly dependent on the number of elements that we are looping through. And we'll be talking in depth about time complexity, what that is, how to define it, and the types of time complexity of different algorithms in the next lecture. So congratulations on solving your first interview question, and be sure to head on over to the next lecture where we're going to be diving into time complexity before we jump into more interview questions. See you there. Hello everyone, and welcome back to our Python interview questions series. In this lecture, we're going to be discussing what is time complexity, as well as the 7 types of time complexity you need to know. We will also be looking at big O notation, defining what that is, and looking at practical Python examples of each type of time complexity and an algorithmic example of each. So first of all, what is time complexity? Well, time complexity is the time that it takes for an algorithm to run. The longer it takes for an algorithm to run, the greater the time complexity. And you want to have as small of a time complexity as possible because that means you have an efficient algorithm that can run fast and can run on large inputs of millions of values, for example. Commonly, time complexity is measured by counting the number of operations that an algorithm will take in order to solve a question, or solve a problem, or print something, execute a statement, etc. And the reason we need to know about time complexity is because by improving time complexity, we can improve performance, because more effective algorithms and efficient algorithms mean better performing applications, software, or wherever you're using these algorithms. Next up, let's talk about big O notation. Big O notation is how you can describe time complexity. That is why we have this O of a value. This is the big O notation for each type of time complexity. And we're looking at the 7 most common types of time complexity that you need to know because you can be asked at the interview test or the whiteboard interview, what is the time complexity of your solution? Alright, so let's start by looking at the types of time complexity. We have them here on the screen in order of horrible to good. So let's go ahead and look at our first type, which is factorial time complexity. Factorial time complexity is represented as O of n factorial. N in all of these cases is the input size For example, if you had an array that you were working with, the n would be the size of the array. All right, so let's look at an example of factorial time complexity. Algorithms that have factorial time include finding the permutations of a string or an array, as well as many algorithms that use the brute force approach, where you try all possible combinations to find the combination you're looking for. The traveling salesman problem, which asks you to find the most efficient path a salesman can take through different cities. Well, if you used brute force to find all the possible paths before choosing the best one, that would take factorial time complexity. Let's build out an example in code of factorial time complexity. I'm going to move this down here and comment out the factorial time complexity and begin with this type. So we can build out an example of a function that calculates all of the permutations of an array. For this, we can define a find permutations function. And permutations means that you are taking a collection of items and you're rearranging them in all of the possible ways they can be rearranged. And we will be talking about permutations in depth later on in this course, so don't worry if you don't understand each of these examples, because we're going to be diving into them deeper in the course, and we will provide all source code at the end of each section as well. So this function can take in an array, which is our collection, as well as a starting index and an ending index. And in order to find the permutations, or all of the ways that the array can be rearranged, we are going to loop through each index from the range of the starting index up to the ending index plus 1, and we must add 1 because this ending value is exclusive. So if we didn't add 1, then the ending index would never be reached. Alright, so in this case, to find the permutations, what we do is we take the array at the starting index, and we take the array at the current index, and we swap the two values. And by swapping the two values, we are going to create one different change, so one different way that we can rearrange the array. To perform swapping, you can state the two values on one side of the equal sign, and on the other side of the equal sign you state the two values again, but in reverse order, separated by a comma. And then after this, you use what is known as recursion. So you call find permutations, the same function inside of itself. That is known as recursion. And we put in different parameters this time. We're putting in an array, the same array. However, the starting index is going to be the starting index plus 1. And we have to put in a new argument here in order for us to go to the next value in the array and then perform the swapping again up to the ending index. And that will allow us to find all of the possible ways that we can swap the elements in the array in order to rearrange them. After this, we also have to backtrack, which means we have to take this line and paste it again as per the rules of finding permutations. And again, we will be looking at permutations later on in this course. But there you have an example of factorial time complexity. Each of these examples is to give you a visualization in code of what the algorithm that has this specific type of time complexity, what it looks like. So this here is factorial time complexity, and this comes from math. You'll find that many of these time complexities, they come from the mathematical steps it takes to create a solution. So for permutations, whenever you need to find the number of permutations, it comes from a mathematical proof that the number of permutations will always be the number of elements in the collection to the factorial. So if we had 3 elements in the collection, the number of ways it could be rearranged would be 3 factorial, 3 times 2 times 1. Alright, that was the factorial time complexity. Now this is a type of time complexity you want to avoid. Why? Because it is slow which means it is inefficient, and it may take so long for a large input size that you could fail the interview test question. Because for many of the questions you get at the test, you will have to solve them efficiently, meaning that they have to be performed within a certain amount of time on a large input size, which is why you want to stay away from factorial time, because it is slow. However, you still need to know about it so that you know what to avoid and you can recognize it. Let's move on to the next type of time complexity on our list, and remember, we're going in order of horrible to good. Exponential time. All right, exponential base 2 time complexity means that the calculations that the algorithm performs are going to double each time that our input grows. So as we get a larger input, the time it takes for the algorithm to compute the result is going to be 2 to the power of the input size. This is also very slow. Not as slow as the factorial, but still horrible time complexity. Examples of algorithms that take exponential runtime are algorithms like finding the power set, which means finding all of the subsets in a set. Now, sometimes horrible time complexity is unavoidable because you may be asked to solve a question in a specific way that will require slower time. However, there are more efficient solutions often as well, which you want to aim for if possible. So whenever you have to find the power set, that will take exponential time, as well as solving the traveling salesman program with dynamic programming. We will be looking at dynamic programming later on in this course, and for now, let's look at a quick example of how we can see exponential time complexity in a coding example. So exponential time, we can build out an example that shows how to get all of the subsets in a set. For example, all of the subarrays in a given array. What we're going to do is use a counter. Say for a counter in the range beginning at 0 up to the power set size. We're then going to go for index in the range from 0 up to the set size. And right now we didn't declare the variables for power set size or set size because we're just looking at an example where we won't be running it. In order to find all of the subsets of a set, this is going to take exponential time because we have to check if the counter and 1 right-shifted to the index, rather left-shifted, if that is greater than 0. Then what we're going to do is print the set at the current index, and we can also add a character break in between each. After that, we can print a line break in between each of the subsets. So we would print a line break like this. So this would be the algorithm for finding all of the subsets of a set. And if you don't know about bitwise operators, such as left shifting, don't worry about that. We will be covering bitwise operators as well later on in this course. And again, this time complexity comes from the mathematical formulas for finding subsets. That is an example of exponential time. So now you have an algorithmic visualization of it. Finding all of the subsets in a set. Again, quite slow. Let's move on to the next type, quadratic time complexity. This is also quite slow, which means it is a horrible time complexity. Quadratic time, this is where the time that it takes the algorithm to perform its operations is directly proportional to the square of the input size. The size squared to the power of 2. For example, if you're working with an array of 3 items, then it will print 9 times. That would be an example of quadratic because it's 3 squared. So An example of quadratic time complexity would be anywhere where you are going through a table structure or a matrix structure or a two-dimensional array, because you have the rows and the columns to go through, which means you have a table to go through, like a multiplication table. And you'll know that the formula for finding the multiplication would be to multiply the rows times the columns, which is a quadratic time complexity, because you're going through all of the elements in each row and each column in each row. Let's build out an example in code as the best way to understand this. Quadratic time complexity is quite common. You'll see, especially for beginners building out algorithms. So suppose we had an array, a two-dimensional array. Maybe for the rows we can have something like 1 as a string, 2 as a string, 3 as a string. And then for the columns we can have something like 4, 5, but each as a string. So we're building out a multiplication table using strings. Well, in this example, what we can do is go through all of the rows and all of the columns in order to print all of the values in the array as a method for finding all of the values in a two-dimensional array. In order to do that, we'll go for row in the range up to the length of the array, and we would say for column in range up to the length of the array at the size of the row, which will return the number of columns. And then we would print the array at the current row and column. So because we're going through a table structure, which kind of looks like this, I can even add more values to it for a better picture. Because we're going through this table, well, the number of steps that we have to go through is going to be the number of rows, 3, times the number of columns, which is also 3, which makes for a total of 9. 3 times 3, and that is that 3 squared up here, because we have this table structure. So that is just one example of quadratic time. The number of steps that the algorithm will take will increase exponentially every time a new input value is added. So also quite slow, but commonly seen, so you have to know about it in order to know what to avoid. Let's move on to linear rhythmic time complexity, O of n log n. This is slightly better than quadratic, but slightly worse than linear. So linear rhythmic is still bad time complexity. However, it is an improvement on the quadratic time. Some examples of linear rhythmic algorithms would be the more efficient sorting algorithms that are used for sorting an array in a particular order. We will have an entire section dedicated to sorting, where you will see the different sorting algorithms, and you will find that the more efficient sorting algorithms will have this time complexity, linear rhythmic. Let's go ahead and build out an example of such an efficient sorting algorithm, which can be an algorithm like merge sort or quick sort, which are different paradigms for sorting an array, which can take quite a bit of time. Let's build out an example. We'll define a function called merge sort, and this will take in an array that we need to sort. And what we can do is check to ensure that the length of the array is greater than 1. And if indeed that is true, then what we can do for merge sorting is merge sorting has specific rules that you must follow that make it merge sorting, as opposed to a different type of sorting. They all achieve the same purpose, but they have specific differences in how they are created and how these algorithms are built. So for merge sort, we have to get the middle of the array, and then we have to divide the array into a left array and also a right array, which will be the array from the middle to the end. Then we will call our merge sort function on the left array, followed by calling merge sort on the right array. And why we do it this way is because this is for better time complexity than if we had sorted the entire array at once By splitting the array into left and right halves, the time complexity becomes better up to linear rhythmic time complexity because other forms of sorting are even slower. So after we have sorted the arrays, we would then loop through all of the values and we would store them into temporary arrays. So we would go ahead and loop through while the left index is less than the length of the left array, and while the right index is less than the length of the right array. What we would do is check if the left array at the left index is less than the right array at the right index. And if so, then what we would do in this case is we would take the array at the current index and we would assign it to the left array at the left index. As well, we would increment the left index. Otherwise, we would do the opposite for the values. We would take the current index and assign it to the right array at the right index. Then we would increment the right index by 1. And as well, after all of that, we would increase the current index by 1. Again, we're going to be covering this in depth later on in this course, but I want you to get a visualization of it up front. As you can see, the complexity of the code is getting a bit higher, and that is because the complexity of the time is getting better. So you'll find that for more efficient time, you'll have to build more complex solutions or higher level solutions than just the straightforward beginner solutions. And that is what differentiates the hired from the unhired. After this, we have to check if any element is left as part of merge sorting. So while the left index is less than the length of the left array, we will take the array at the current index and assign it equal to the left array at the left index. We'll also increment the left index and the current index. Then we would perform the exact same thing but for the right index. So while the right index is less than the length of the right array, we're checking for any values that are still left that we have to sort into a specific order, like ascending order. So we would assign the value and increment the right index to ensure that we go through all of the indices left. That is an overview of merge sorting, and there are proofs that you can find that will prove that it has linear rhythmic time, and this involves an understanding of math. I highly recommend that you look into those as well. As we do more problems, you will also be able to recognize the patterns in time complexity as well. So definitely solving more problems is not to solve the specific problem itself, but to learn to recognize patterns in problems, because that way at the interview test, you'll be able to boil down the problem to the pattern that you'll recognize, and that will give you the power to solve any problem that they throw at you at the test. All right, so that was linear rhythmic time complexity. Let's go back to our list down here. We have left linear, logarithmic, and constant. Now this is where we get into better time complexity that we want to aim for. These are the more efficient types. So we're going to pause this lecture here and we will look at these three in the next lecture because we've covered enough for now. So be sure to head over to the next lecture where we're going to look at the types of time complexity you want to aim for. Congratulations everyone on learning the valuable types of time complexity that you need to know. The types so far we've seen are ones that are slower. Head on over to the next lecture where we'll be looking at more efficient types. See you there. Hello everyone, and welcome back to our Python interview questions series. In this lecture, we're going to look at the types of better time complexity, which means the algorithms that run faster. In the previous lecture, we covered the 4 types of time complexity you need to know how to recognize and how to avoid. And in this lecture, we're going to look at 3 more. So let's begin with linear time. This is fair running time, which means it is not good, but it is fair. Linear time. This is where the time that it takes for an algorithm to execute and return a result will be directly proportional to the number of input, so the size of the input. As the number of elements in the input increases, the number of steps for the algorithm will also increase directly. These algorithms with linear running time are very common, and they imply that the algorithm is going to visit each element in the input. Examples of algorithms that have linear time complexity would be examples and algorithms that are looking at finding the maximum and minimum value in an array. That would require linear time complexity. Now, this can also be part of a larger question. One question may have a sub-problem that requires you to find the maximum or minimum value in an array. And so the overall time complexity of the entire solution would be multiplying each time complexity. For example, if you had linear time complexity in one function and then logarithmic time complexity in another function, then you would have to multiply the two time complexities together to get the overall time complexity of your entire program. But linear time complexity is also found in its own solutions. Another example is if you have to find an element from a collection. Some algorithms that do this can require linear time, as well as printing all of the values in the collection or list. This would take linear time. Why? Because you have to print all of the values, which means you're visiting each value. Let's go ahead and look at an example. We can look at an example where we are finding the maximum value of a randomly sorted array. So we can build out an array, and perhaps it has a bunch of random values in weird order, and we have to find the maximum from this. Now, of course, with every question there are many ways to solve it, and some algorithms can take linear time to solve this. So we will build one variable called overall max, and that will be 0 initially. And what we'll do is we'll loop through each index in the array, and we will go up to the length of the array. And what we'll do is we will check if the array at the current index is greater than the overall max. That means that we found a new maximum for our overall calculations, which means we have to change the overall max value to equal the array at the current index. This will happen when we reach the 3 and the 5 and the 7, and it will stop at the end of the array, which means we'll be left with 7. Alright, and that is linear time right there, because you're visiting each element in the array. If I added more values to this array, well, suddenly my time complexity has increased by 3 extra steps. Let's go ahead and look at the next type of time complexity, and that is logarithmic time. This is an example of good time complexity. Yes, we're just now getting into good time complexity as the 6th one on our list here. This type of time complexity scales well, which means that if you have a huge input size, logarithmic algorithms would be efficient. One example of a logarithmic algorithm is a binary search algorithm. This uses the divide and conquer algorithmic paradigm, which we will be covering later on in this course. Divide and conquer, for an overview, it means that it breaks down a problem into sub-problems in order to improve the time complexity and make the solution more simple. And binary search will search through elements in an array, and it will do this using divide and conquer. For example, if you wanted to look for a word in a dictionary, well, instead of looking through all of the words in the dictionary at random, you can instead sort the dictionary into alphabetical order. And if you know that the word begins with A, well, then you only have to look at the A part of the dictionary. You don't have to look at the entire dictionary. And there are other ways that we can also solve this, like we split the dictionary in half, and we then look through the right half or the left half, depending on if our word begins with K to Z or A to K. Alright, so let's build out an example of binary search. I'm going to define a new function called binary search, and this could take in a number of parameters. Let's put in the starting index, the ending index, the array itself, and the element that we're searching for in our search. First, we'll check the base case. We always want to check for validation. We want to make sure we don't allow negatives, nulls, etc. So if the ending index is greater than or equal to the starting index, that is the validation we want to check. And what we'll do is we'll set a midpoint of our search, our array. In this case, we're searching for a value in an array. So what we'll do is we'll split the array into two, and then we'll look through the two halves. So to get the middle of an array, we take the starting index and we add the ending index minus the starting index, and we divide it by 2. Then we're going to first check if the element we're looking for, if it happens to be the middle itself, well then we got lucky and we don't have to perform anything else. We can just take the array at the middle and we can check if it equals the element, and if so, we'll return the middle. Now, here's where we get into divide and conquer. If the element is smaller than the middle, then that means it can only be in the left half of the array, because we're assuming this array is sorted. And of course, we can also sort the array initially if we need to. So if the element is smaller than the middle, then we don't have to search through the entire array, we can just search through the left half. Similarly, if the array is bigger than the middle, then we only have to search through the larger half of the array. So as you can see, we are decreasing the number of steps that we'll have to take. So we'll add a check elif, elif the array at the middle is greater than the element. That means that we're going to call recursively binary search on the left half of the array, because we don't have to search through the right half. So we're going to put in the array and the same starting index, but the ending index now is going to be different. It will be the middle minus 1, because we're now only searching through the left half. And because this is recursion, that is where we get into the log n time. The element is still the same, so we put that as the argument. Now we can add an else statement. If the first condition did not pass, or the second one, then that means that the element must be in the right half of the array. So we're going to return a binary search on the array, but the starting index is going to be the middle plus 1, because now we're looking through the right half. The ending index is the same, and so is the element. Now, if the ending index was not greater than or equal to the starting index, well, we also want to make sure we account for that case. So we're going to add another else statement, and we're going to return -1, because that means there's no way that we could find the element in that array, and that also means that the element was not even found in the array when we recursively call it. Alright, so that is an example of logarithmic time complexity. Next, let's talk about the last type of time complexity on our list. We've gotten to constant time. This is good time complexity. Constant time is what you want to aim for. Constant time, notice that there's no n in the big O notation here. That is because constant time is not dependent on the input size. It is independent of the input size, which means the algorithm with constant time will always execute in the same time, regardless of how huge or small the input size is. If there is one element that we are looking for, or if the array has only one element, then the algorithm will take 0.01 seconds to find it and to execute. Or if the array has 1,000,000 elements, then the algorithm will still take 0.01 seconds regardless. And how do we achieve constant time? Well, we achieve constant time by building solutions that only take one operation, one step. So, examples. would be questions that ask you to find if a number is even or odd. Because you only need one step on one number, that means constant time. Another example is checking if an item in an array is null. The array might have 1,000,000 elements in it, sure, but because we're only checking one item, that is constant time. It doesn't matter how long the array is, we're only looking at one item. Another example is finding a value from a map, because again, you are only looking at one item. Another example is printing the first element in an array, because we don't have to traverse through any others. Not only that, but also efficient constant time can be found when you use bitwise operators and when you use high-level math solutions that implement math strategically. And we will be covering those strategies later on in this course as well. So constant time, let's build out an example of the type of time complexity we want to aim for. We're going to define a function called isEven, and this will check if a number is even. And you'll see how this will only take one operation, therefore it is constant time. If the number mod 2 is equal to 0, that means that the number divided by 2 leaves no remainder, which means we can print even. The number is even. It goes cleanly into 2. Otherwise, the number is odd, because that means it does not go into 2 evenly. As you can see, we have only one operation being performed. We're only printing one time. And we're only checking one element. That is constant time. Congratulations everyone, you just learned about the 7 types of time complexity you need to know for the interview test. And throughout this course, we're going to be discussing time complexity of the questions that we go through. That way, you'll be able to recognize patterns of time complexity where the same time complexity shows up over and over again. And in this way, you'll be able to recognize the different types in different examples. There's also space complexity, and space complexity is the space in memory that is taken up. So we're given an input of a number, for example, and if we were to use a string or an array or a table to solve this question by building out a new variable called var check evens or something like that, but we wouldn't use the var keyword. If we were checking for evens with a variable, because we are building out a new variable, that would take up space in memory, especially if we're using something like an array or a table. If you're building out a new table, that is going to take up memory. Therefore, it's going to take up space. And if it's a table specifically, it would take quadratic space because it would create a table. O of n squared is quadratic time complexity, and similarly, O of n squared can be space complexity. So space complexity is similar to time complexity, however, whereas time complexity is the running time, space complexity is the memory used. And often you can require no extra space complexity by just manipulating the input and not building out any extra space in memory with variables. We'll be looking at space complexity as well throughout the different questions. Congratulations everyone on solving this lecture. In the next lecture, we're going to jump into solving questions in our first section of the top 10 most popular topics that you will be asked about. Thank you all for watching, and head on over to the next lecture. Hello everyone, and welcome back to our Python interview questions course. In this lecture, we're going to be starting our string and array section with the reverse words interview question. The question asks you, given an input string, reverse the string word by word. So we would have an input such as reverse words in a string, and the output we would need to produce is strings A in words reverse. All of the words are being reversed rather than the characters. Of course, there are many ways to solve each problem, and an efficient way to solve this problem is to loop through all of the words in the string and insert them by looping backwards. So let's go ahead and first build out a string, and we can put in that sample input reverse words in a string. Then after that, we can go ahead and make a words array, and this is going to be the string split at every space, just like that. Then after that, we can go ahead and assign our string to be an empty array. So we're going to need a new variable here called string array, and this is going to be an array into which we will put the words in reverse order. So what we're going to do is make a for loop, and we can go for each word in words. What we will do is take the string array and insert into it the word. And then finally, to test our solution in the console, we can print out the result by joining up all of the values in the string array and printing it as a string. Okay, that is all that you need to reverse words in a string. Let's go ahead and test this out by pulling up the console and hitting run. And as you can see, we have being printed in the console, string A in words reverse. That is exactly what we expected, which means that we successfully solved this interview question. As for the time complexity, because we are looping through each word in the string, the time complexity is going to be directly dependent on the number of words in the string, so it will be linear O of the number of words in the string. Thank you all for watching. Congratulations on solving this interview question. We will see you in the next lecture, where we're going to be continuing our section looking at string and array interview questions, one of the most commonly asked sections and categories at the interview. Thank you all for watching, and we will see you in the next lecture. Hello everyone, and welcome back to our Python interview questions course. In this lecture, we're going to be solving the rotate array interview question, which asks you to rotate an array of n elements to the left by k steps. You may also be asked to perform right array rotation, which we will also briefly cover as well in this lecture. Left array rotation is where you take the first k elements in an array and you rotate them to the end of the array, as exemplified here on the screen. If the question asked you to perform right array rotation, rotating an array of elements to the right, then you would take the last k elements in the array and rotate them to the front of the array. Let's go ahead and look at how we can go about building this solution. So we can go ahead and loop through all of the elements up to the kth element and then move them to the end of the array. So let's go ahead and start building out a solution down here. We're going to build a method called left rotate array, and it's going to take in an array as well as the k value. And what we're going to do is first store the size of the array in a variable that will store its size. So I'm going to go ahead and initialize the variable and initialize it to be the length of the input array. Now that we have the size, this will allow us to loop through all of the elements in the array. Okay, the next step is to take k and take the modulo of k against the size. This will allow us to find the greatest common denominator between k and the size. After this, we can go ahead and assign that greatest common denominator. And this is going to be equal to a helper function that we'll have to build called find greatest common denominator. Let's see, denominator. And this method is one that we're going to build, and it's going to take in k as well as the size. So let's implement this method immediately. You can do that just above here, above the left rotate array method. We're going to implement another one, and this is going to be called find greatest common denominator. This will take in two values, x and y, and find the greatest common denominator between the two. So first we're going to perform a check. If y equals 0, then we're going to return x. Else we're going to return the find greatest common denominator of y and of x mod y. That is all you need for finding the greatest common denominator. Now that we have implemented that method, we can come back down here and we'll be able to use it. Okay, right now we're getting a message that we haven't used the greatest common denominator variable. So let's go ahead and use it. We're going to go ahead and loop through all of the elements in the array up to the kth element. So I'm going to open up a for loop for this, and this is going to be for index in the range of up to the greatest common denominator. And we have opened up a loop just like that. And inside the loop, we're going to move a block of the array up to the kth element. In order to do that, we're going to have to store the temporary value of the array at the current index. And we're also going to store the current index as the index we are currently at. Then we're going to make a while loop, and we're going to declare a variable called index plus k. This will be equal to the current index plus k. And then after that, we're going to check if index plus k is greater than or equal to the size of the array itself. In that case, we're going to assign index plus k to equal index plus k minus the size. Now this is accounting for the edge case where suppose we had k being 14, but our element only had 5 elements, our array only had 5 elements. Well, if that were the case, then we would have to go ahead and rotate several times, several 360-degree rotations. And that is what we're accounting for with this first if statement here. Now that we have that accounted for, we can perform another check. We're going to check if index plus k is equal to the index. If that is the case, then what we're going to do is break out of the looping. Next, the step is to take the array at the current index, so the current element, and assign it to equal the array at index plus k. And finally, we can assign the current index to equal index plus k. This way we will not end up with an infinite loop. As well, we can take the array at the current index, and we can assign it to equal the temporary value. And that is all that you need in order to rotate the array. Let's go ahead and add another helper function, and this is going to print out the array for us. So I'm going to add that after the current function. I'm going to print an array, and it's going to take in the array as its parameter. I'm going to get the size of the array with the length property, len of array. And now that we have the size of the array, we can go ahead and loop through all of its elements. So we're going to say for element in range of size, what we're going to do is print in decimal format. What we're going to do is print out the array at the current element, the array at the current element, and we're going to add a space in between each of the characters, each of the elements. Okay, excellent. That is all that we need to print out the result. So let's go ahead now and test this out. Let's build an array. We can use the exact same array we had at the beginning of this lecture, right here. So let's go ahead and use that for our example, and we'll perform left rotation on it. So I'm going to open up a new variable called array, and then I'm going to call left rotate array, and put in the array as well as 2, which represents k. And after we have performed left rotation on the array, we can go ahead and print the array with our helper function print array. Alright, let's go ahead and pull up the console now and test out this code. I'm going to hit run. And as you can see, we have 3, 4, 5, 6, 7, 1, 2 being printed in the console, which is exactly the array left rotated by 2, which means we took the 2 first values in the array and we left rotated them, moved them to the end of the array. Again, if you get a question of right array rotation, that means you would have to take the last 2 elements and rotate them to the front of the array. So just the opposite of what we did. And I encourage you to go ahead and manipulate this answer and edit it so that you can allow for right array rotation. That will be a good challenge for you to practice in order to ensure that you know how to perform array rotation. Other than that, thank you all for watching. The time complexity for this solution is going to be linear because, as you can see, we'll come down here and we are looping through each element in the array up to the kth value, which means that the time complexity will be linear dependent on the number of values that we have to rotate, that k. We didn't use any extra space because we didn't make any new arrays. We just worked with the input array. That means we have constant space and we didn't need to require any more space in memory. Thank you all for watching. We're going to be continuing our look at strings and arrays in the next lecture, so we'll be sure to see you there.
Hey everyone, thanks for watching this course. If you want to watch the rest of the course, the link is down below. Not only do we get the access to this course, but you'll get access to a lot of other courses in a huge bundle, and it's on sale today. So buy before the sale ends. Thanks for watching, and I'll see you in another video.